4. Okay. Booster.
Oh, no, that's not too bad. Yeah. Yeah, I'm gonna do much more. So we can show lots of stuff, and then it goes some more stuff without. And then we do stuff on.
Yes.
So last week, in the tutorial, tutor said he would upload a solution from email us and find some way to on Discord. He's still being able to
Send him an email and I'll do the same. So I got a question on that by email yesterday and said, talk to Jack. Okay, but I'll contact Jack. Good. Okay, I'm not going to finish lecture 14. Look at the notes. Basically, counting microstates leads to an equation that is effectively the Tetrode-Sakura equation for an ideal gas. I believe you'll do that again with Julian later, more thoroughly. So I want to just go straight to the point. I've got 2 lectures left. Really look at statistical mechanics, its own fundamental postulate, and how we get from that to entropy, microstates, temperature, thermal equilibrium. So what is this fundamental postulate or assumption? So basically it's an assumption. So what this is that a closed system is equally likely to be in any quantum state, and by quantum state, interpret that as microstate, accessible to it. Okay? So what I mean by that is that all accessible quantum states equally probable. Okay? And this is also true for classical system. So that's my fundamental postulate. There it is. That all microstates that are accessible are equally probable. Okay, looks innocent. I've mentioned in there a closed system. So what is this closed system? What I mean is that U, V, N, all constant. Okay? And if I have other things like G, B, E, all constant, if relevant. Okay, so basically a system that has its independent parameters fixed. Okay, so I talk about accessible. What is this thing accessible? So I can say a quantum or classical state is accessible if its properties are compatible with the specification of the system. So what do I mean by that? I mean that something like energy in range U to U plus delta U, etc. Okay, and note for a large system, things like the U on U are going to be tiny. Okay, the n on n, tiny. Okay, so I'm really dealing macroscopic systems. So macroscopic description, the compatible micro states or quantum states are things that are compatible with these constraints. Okay, so we've got that far. Next, for a given macro state. So the macro state is described by volume, total energy, etc. Okay. So macro state with energy between U and U plus delta U. The number of microstates accessible to it is omega U. I'm going to use that symbol. And since all microstates are equally probable, then I can say that probability of being in a particular state is equal to 1 over omega U. Okay, so that's the probability of being in the ith state. Okay, so they're all equally probable. So this is all fluffy. And that means that the sum of all probabilities for all the microstates, so I is an element of omega U, equals 1. Okay, so if I add up all the states, the probability is 1. Each of them has the same probability, 1 over the number of microstates. Sum of the probability of each microstate compatible with the macrostate. So totals 1. Okay. Okay. Yeah, chat question. Is everything from lectures examinable in midterm? No. Let me decide what the midterm test is, and I'll talk about it next lecture. Okay. Hasn't been written, so you get a fresh test. Okay, so I've got that. So now I want to get into the heart of things. Let me go to a new piece of slide, because this is important. So, for system where energy constrained, so it's going to be somewhere between U to U plus delta U. There may be many or various microstates. No. Sorry. Should be careful. Go away. Wrong. Various macrostates. Okay, various macrostates with the same energy. But differing other macroscopic parameters. So by this, I mean it could differ in pressure, temperature, volume, etc. Okay, so you've got energy constrained, but various different macro states that vary the other parameters. Okay, so here's the big one. The most probable macro state specified by the unconstrained parameters and those parameters are again e.g. P, T, V, etc. will correspond to that state with the largest number of accessible microstates. Okay, so this is the big idea. That if I have a system where I have one macroscopic parameter fixed, say energy, and I have some of the other parameters like volume or pressure, temperature that can vary, the most probable macrostate is the one that corresponds to the largest number of microstates. Okay, so this is my approach to equilibrium. Okay, so the macrostate will change in time. Until the number of microstates compatible with the macrostate reaches a maximum. Okay. So basically your macrostate changes so that the number of compatible microstates is a maximum. And at this point, system will be found in any microstate accessible to the final macrostate. Okay. So this is the whole show. Yes. This is a unique global maximum. It is equilibrium. Okay. If it's not unique global maximum, then you haven't found it yet. You still got to keep looking. Okay. So this is the guts of all of statistical mechanics. Find the macrostate that has the largest number of microstates. Okay, example. So we had the adiabatic free expansion. Let's just go straight back to the old example. We've got a box. We've got a volume of gas, we've got a vacuum. And then we pop the partition. And we have V dashed equals alpha V. Okay, it's expanded. And this was initial, final. This is irreversible. So I count microstates. Omega compatible with the energy initial is going to be proportional to the volume to the power of n. Okay, so n equals the number of particles. Because each particle can be anywhere in that volume. But omega u final is going to be proportional to alpha v to the power of n, and this is much larger by alpha to the power of n. Okay, so n is going to be something enormous. So with the system will go to the macro state with the biggest number of microstates, which means gas spread out everywhere. Okay, so now I want to look at what does this tell me about equilibrium. So I'm going to play with an example first. Thermal equilibrium. Two interacting spin systems. So this is an example just to get a flavor of what's going on. The argument I'm going to eventually make is completely general and does not depend on this at all. Good. So I've got two systems and I bring them into thermal contact. Okay. So energy can be transferred. So this implies energy can transfer between two systems. Okay, so the important word is thermal contact. Okay, that is equal to that. Okay. So the two systems form a larger system. And for the larger system, I can write energy is equal to energy of subsystem 1 plus energy of subsystem 2. So when I do that, I bring these two systems together. The question is, which way will energy flow? Questions. Which way will energy flow? I put two systems together. One has more energy than the other. Yeah, good guess, but it actually is not necessarily so. It's going to depend on all kinds of other parameters. I could have a very small system that is at a very high temperature, but it's very small, and a monstrous system at low temperature, but it has net energy massive because it's huge. The energy will flow from the little guy to the big guy. So it depends. So it's not so simple. So answer, not simply from high U to low U. Okay? So depends on the size of the system. So it depends on size and other parameters. So it's not so simple. Okay, done that. Let's do it. So I have two spin systems. There's number one. Put it in a styrofoam box. And there's number two. Put it in a styrofoam box. Okay, so I've got U1, number of spins 1, U2, number of spins 2. I apply a B field. So I line my spins, I insulate, isolate. Okay, they're just separate. And then I have a combined system. So the combined system, I now stick them together. I've got a giant insulating, isolating box. And now I put diathermal wall. So this will allow energy to pass between the two systems. So allow energy transfer. And I still have, oops, magnetic field. I still have U1, N1, U2, N2, at least initially, okay? So I let the system exchange energy. Okay. So I'm looking for the most probable final division of energy. And this is the one with the maximum number of microstates. So most probable final division of energy is the one with the maximum accessible microstates. So that's the criterion I've got to use. So before I get to that, I can ask the question, how is energy transferred in this example? So I've got a constraint that U is equal to U1 plus U2. So how will energy be transferred in this? While keeping energy fixed. No, these are just spins. Yeah. Yep. So coupled spin flips. That's the way it's going to work. So each spin flip gives me delta U 2 mu B. Okay, because it's flipping from aligned with the magnetic field to anti-aligned or the other way around. Okay, so what this gives me is that energy exchange by coupled spin flips. Okay, so I can do something like this. Again, example. So I start off with my, this color maybe. Is my partition. I start off bang, 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 bang. This is 1 and this is system 2. I've got my B field. And then I move to this state where one of these guys has flipped down and correspondingly they've flipped up. Okay, So this is a possible energy exchange. So given that I can do that, I now need to find the energy exchange that leads me to a state which has the maximum number of microstates. Okay? Yes. Yeah, good question. This is a toy system, okay? It's going to require some coupling between the magnets so they know about each other, but this is really a toy system, okay? So now let's get to a completely general argument. So completely general argument. Actually, spins do flip. Nuclear magnetic resonance. In a nuclear magnetic resonance experiment, you do a thing called magnetization transfer, and you excite this spin to flip and cause this one to flip. So the way the guys do the experiments in an MR is they prod a certain spin to flip and then see what the neighbors are that are coupled to it. So you have a thing called J coupling. It gets out of my depth, but this is the experiments they do. They actually cause cascades of spin flips. But okay, I leave the spin, completely general. I can say that total number of microstates for a combined system. So the only assumption I'm making here is I have two systems that I'm pushing together. The total number is going to be number of microstates total is going to be equal to the product of the microstates in system 1 with the microstates in system 2, where U equals U1 plus U2, and that is constant. Okay, question. Why the product of microstates each subsystem? So why the product? Yeah.
You normally product stuff together if there's each individual one is up and down. You may as well just squish them all together.
No. Yeah. Yeah, so for each state of one subsystem, you can have any of the states of the other one. So you multiply them. So it's basically because they're independent. So this is really important. That multiplication is where we go. So basically, since every microstate of subsystem 1 since every microstate substance can coexist with every microstate of 2, okay? So that's why it's the product. So now I go to my fundamental postulate. So the fundamental postulate just says that equilibrium is exactly the same as omega u, number of microstates is maximum. So now all I've got to do is to find where this guy is maximal. So I've got to add with energy exchange between subsystems to achieve my maximum. Okay. Actually, let's be explicit. Omega u maximum. Okay, so I've got to exchange energy until this reaches a maximum value. That's all I've got to do. Okay. How do I find a maximum for this equation? Differentiate it and find where the derivative equals 0. So it's very simple calculus. So at equilibrium, this implies that the omega u, u1, is equal to the omega u, u2 equals 0. So I have that condition, and the only other condition is I need to show that it's a maximum and not a minimum or a stationary point. With condition, the u1 plus the u2 equals 0, since u is constant. That's all I've got to do. Okay. I can't do these derivatives, but I can say that since big U, number of microstates in this, is equal to number of microstates in system 1, product number of microstates in system 2 at energy 2. I've got that. I just substitute that in. So this gives me that, the omega u, the big one, the u1, is equal to omega 2, u2, d omega 1, u1, du1. Okay, I've got that guy. But I get another term which is a bit ugly, plus omega 1, u1, d omega 2, u2, du1. Okay. So I've got a mixed derivative at the end. I'm going to have to deal with that. Before I do that, I pull a trick. Divide by omega 1, u1, omega 2, u2. Okay, I do that to get a simpler form. So just do that. So all of this is equal to 0. So if I divide by that, I don't have any problems. So divide by it. And now I get 0. So I'm bringing my 0 around there, equals 1 over omega 1, u1, the omega 1, u1, du1. That's nice. And for the second term, I get 1 over omega 2, u2. But I've got this ugly mixed derivative. How do I fix that? Okay, let's not fix it then. Leave it. I don't want to differentiate something that's a function of u2 by u1. So instead I differentiate with respect to u2 and multiply it by du2 du1. So I can do this as the omega 2 u2 du2 times du2 du1. Okay, is that clean? No cheating, okay? Do you recognize this? What is this? It's a perfect derivative. In fact, I've got an integrating factor out the front. It's the log, okay? So this is just a log. So it's derivative of ln. So now I get a very nice equation. I get that 0 is equal to d log, d log omega 1 u1 du1 plus d log omega 2 u2 du2. And this is multiplied by du2 du1. Okay. What do I do next? I've got this equation here. So I can use that equation there to give me that guy. Okay. And by looking at that, what's that going to be? -1. Okay. So at this point, I get magic. So I say, but u1 plus du2 equals 0. This implies du2 over du1 equals -1. And this gives me an amazing equation. The derivative of the log of the number of microstates in subsystem 1 du1 equals d of the log of the number of microstates in system 2 at u2 du2. And that's my equilibrium condition. Okay, so this is pure magic. It's telling me that my equilibrium condition is that the log of microstates du has to be equal for both of these. Okay, and this is a completely general argument. Okay, so it has nothing to do with spins. What is this telling me? What is the normal thermal equilibrium condition? Two systems are in thermal equilibrium when temperature is the same. So what has that got to be telling you? That's got to be equivalent to temperature is the same. So if that's saying temperature is the same, what is ln omega? It's not the temperature. It's not Q. The entropy. Okay. So let's compare to, let me lead you through that. This is why we did this classical thermodynamics. So I'm going to compare this to classical thermodynamics. So at thermal equilibrium, I've got T1 is equal to T2. So this equation must be equivalent to that. And I developed this formal structure. So the formal structure was that temperature of system 1 is defined as the U1, the S1 at constant V1, N1, okay? And the U1, the S1, V1, N1 is equal to the U2, the S2, V2, N2 at thermal equilibrium. Okay, so I've got to compare that. Compare these. Okay. What's going on in these two equations? Are they the same or are they different? Same or different? They're inversed. What does that mean? Entropy representation. So if I go, or in entropy representation, I have 1 over T1 equals 1 over T2 at equilibrium. And I have the S1, the U1 at V1, N1 is defined as 1 over T1. Okay? So basically what you saw on that other page was 1 over the temperature or something proportional to it. So now I connect classical, thermodynamics to microstate perspective. And I get that 1 over the temperature is within a constant of the ln omega as a function of u, number of microstates, du. And my entropy is equal to K times the log of the number of microstates. And I say where K is the same as KB is Boltzmann's constant. So this is the big equation, okay? There is entropy, the log of the number of microstates, just multiplied by a proportionality constant. Yeah? How did I work it out? All I did was I said that equilibrium in thermodynamics has to be the same as equilibrium in this new thing called statistical mechanics. The equilibrium condition, thermal equilibrium condition, must mean the same thing. Therefore, it's got to be the same equation, except for proportionality constant. Okay, that's all. So entropy is K log omega. Boltzmann kills himself. What's carved on his grave, his headstone? That equation, okay, but in a slightly different notation, okay? So he died for entropy. Okay, so I'm telling you, this is entropy. Does it have the right properties? It's not worth it, yeah. It wasn't. I think he was a complex person. Brilliant people are often outside the bell curve. They're in their own space. He was one of them, and that's how it goes. So does K-log omega have the right properties? For entropy. Okay. Okay, so if I have a composite system, number of microstates is equal to U1 times U2, omega 2, U2. Okay, that's for a composite system. Okay, so from that, I just take logarithms. So I get ln omega u equals ln omega 1 u1 plus ln omega 2 u2. So this gives me that entropy total is equal to entropy 1 plus entropy 2. So it's additive, extensive parameter. Okay. So it's got the right stuff. One more thing. Because of the way this was discovered, there's another notation you need to know about. The ln omega du. That's the same as 1 over Boltzmann's constant times the temperature. And that often, for convenience, this is defined as beta. So beta called the temperature parameter. So this beta is still used because it saves writing 1 over K Boltzmann times the temperature. Okay, so this is my entropy. So let me write it in one more slide just to drive it home. Entropy is proportional to the natural logarithm of the number of microstates. Okay, accessible to a system. Okay, S equals K ln omega. Let me make that nicer. Okay, there it is. That is what entropy is. Okay, is that enlightening or no better than where we were last week? Yeah, it's not massively clearer because it's just pushing the can down the road. Why is it that way? Why should the natural logarithm of the number of microstates go to a maximum? Why should that increase? So the argument is basically probabilistic. The system will move to the most probable configuration, and that happens to be the one with the maximum number of microstates. So it's all based on probabilities. What do you mean? Basically, you're counting numbers of states. So in a spin system, if you've got a net magnetization, you're counting how many ways can you get that net magnetization from the individual spins. So for your ideal gas, you're thinking of boxes in phase space, and you're thinking of the number of ways you can configure your particles in to get you those boxes in phase space. Okay? So it's really just counting states. Just one more slide before I kill it. Ways to increase. So this might bear on what you're saying, entropy. So entropy is maximizing number of microstates. So if I have a box and I want to increase entropy with the same box, keep the volume fixed, I can add more particles. So add particles. So N increases and S increases. Okay, so it's one way. I can have my box again. How many boxes do I want? 1, 2, 3, 4, 5. That's about right. So I can have the same number of particles. But I can add energy. So add energy. So U goes up, S goes up. I can increase the volume. We did that for the free expansion. Leave everything else fixed and just increase the volume. So in this case, I've got 3 particles. In this case, I've got 3 particles. Okay, so I increase volume. V goes up, entropy goes up. Okay, I can start becoming a chemist, play with chemical potential. So again, my insulated box, I now have particle, but this guy is composite, and I decompose it. So in this case, I decompose molecules. So I change chemical potential, but I'm not sure which way it goes. Okay, so I don't want to get lost there. And I deal with proteins as a professional. So for a protein is a polymer. And if I have a polymer, I can go from, say, a rigid polymer to a squiggly polymer. So in this case, I'm allow rigid polymer to go to flexible, and S goes up. Okay, but each of these ways of thinking about it, all you're doing is increasing the number of microstates accessible. Okay, that's the common theme. Any of these processes, are increasing number of microstates. And it's got to be log of microstates because it's got to be extensive. It's got to be additive. Okay. If you learn anything from this subject, this is the lecture. Okay. Any questions on anything? Yes. I think I'd have to think about it very carefully. So if you increase the interaction massively, you will reduce entropy. You will reduce the number of allowed configurations. Yeah. Yes, I think your logic is roughly right, that it will actually, increasing the interaction strength will decrease the entropy. Okay. So if you could do that. Yeah, but you got to be very careful because it depends on what else it does. Okay. So interactions are not just isotropic. Any other questions? Yes. It's a general equation now, okay? But if you have a fixed energy, it's for the fixed energy. If you don't have a fixed energy, suck up energy from other places, increase omega, okay? But you got to consider the whole universe, what's going on. Yes. No, it doesn't have to be. I think for simple quantum systems, yes. For a classical system, it's continuous. Yeah, you've got the way you count microstates in classical statistical mechanics is to do integrals of functions. Okay. Yeah, you chop it up in little boxes, but you take the boxes to 0. Okay. Good. Okay, last lecture for me on Friday. Any questions about mid-session tests? That's the time to ask. Okay. Let me just do what I've got to do first. And done. Okay, stop sharing. And